Welcome. Check out the safety tips and be sure to subscribe to the channel right here. Thanks for watching.
You are looking at an object that can release more energy than a bomb in a fraction of a second. It's inside refineries, food factories, and hospitals. And most people never knew they were standing just a few feet away from something capable of destroying an entire city block. Hey everyone. I'm Eric, your workplace safety expert. And in this video I'm going to show you something that completely changed the way I look at industrial facilities. Stay with me until the end, because the real case study I'm about to share with you is one of the most chilling stories in modern industrial history. Let's go. Let me tell you something that kept me up the first night I truly learned about this. There is a piece of industrial equipment so common that it exists in virtually every major industrial facility in the world: oil refineries, power plants, pharmaceutical factories, food processing plants. And this equipment operates under extreme conditions of pressure and temperature that, if they go out of control for just a few seconds, can generate a catastrophic explosion equivalent to tons of conventional explosive. That equipment is called a pressure vessel, and in this video I'm going to show you exactly how it works, why it is dangerous, what American standards exist to protect human lives, and the most terrifying case study in recent US industrial history: an accident that killed 15 people and injured over 170, not because the technology failed, but because the warnings were ignored. A pressure vessel is basically a closed container designed to store gases or liquids operating above normal atmospheric pressure. Sounds simple. Sounds harmless. But once you start understanding the numbers behind it, the picture changes completely. We're talking about equipment that operates with internal pressures of hundreds or even thousands of pounds per square inch, what engineers call PSI. To give you a real sense of that scale, a standard car tire runs at about 35 psi. An industrial pressure vessel can operate at 1,500, 2,000, or even 3,000 psi. That is raw compressed energy, contained inside steel walls calculated to millimeter precision. And what happens when that containment fails? The answer is simple: all that energy released instantaneously turns into destruction. And I'm not talking theory here, I'm talking real accidents, with real names, real dates, real families who lost everything in a matter of seconds. But before we get to the most shocking case I'm going to show you, you need to understand how this equipment works and why it exists. Pressure vessels exist because modern industry needed a way to store and process fluids under controlled pressure and temperature conditions. In oil refineries, for example, they're used to separate crude oil into useful fractions: gasoline, diesel, kerosene. In food processing plants, they appear as autoclaves for sterilization. In power plants, they show up in boilers and steam systems. In the chemical industry, they are the reactors where pressurized chemical reactions take place. Without them, a significant portion of modern civilization would simply stop functioning. But with them, there is a permanent risk that demands rigid standards, constant inspections, and an unshakable safety culture. The types vary considerably. There are horizontal, vertical, and spherical vessels. Heat exchangers, where two fluids swap thermal energy without mixing. Separators, which split gas and liquid mixtures. Reactors, which contain pressurized chemical reactions. Each one with its own design characteristics, its own specific materials, and its own potential failure points. And every potential failure point represents a real threat to the lives of those who work around that equipment. The failure mechanisms are what fascinate me, and at the same time, deeply concern me. Brittle fracture happens when the material gives way suddenly, without warning, like a glass breaking. Corrosion eats away at the metal from the inside over years, reducing the wall thickness to a point where it can no longer withstand the internal pressure. Fatigue from repeated cycles of pressurization and depressurization creates microcracks that grow silently over time. And overpressure, when the internal pressure exceeds the design limit, can occur in minutes if the protection systems fail. The worst part? Many of these mechanisms are invisible to the naked eye. You cannot see internal corrosion. You cannot see a microcrack growing. And by the time the problem becomes visible, it is often too late. Now I need to tell you a story that most people have never heard. At the start of the 20th century, the United States was living through an explosion of industrialization. Steam boilers were everywhere: factories, ships, locomotives. And they exploded with terrifying frequency. It was not uncommon to open an American newspaper from 1900 and find headlines about boiler explosions killing dozens of workers. There were no standards. There was no code. Each manufacturer built however they thought was right, and workers paid the price with their lives. In 1905, a boiler exploded in Brockton, Massachusetts, killing 58 people and destroying an entire shoe factory. That was the turning point. Public pressure forced American states to take action. And in 1914, the American Society of Mechanical Engineers, the ASME, published the very first boiler and pressure vessel code in history. A document born from the blood of dead workers that, more than a century later, remains the global reference standard for pressure vessel safety. The ASME BPVC, as it's known, is not a simple document. It is a collection of sections covering every aspect of a pressure vessel's life cycle, from design all the way through in-service inspection. Section 8, which deals specifically with pressure vessels not subjected to direct flame, is arguably the most cited engineering document in the global petrochemical industry. It defines how to calculate the minimum wall thickness, what the maximum allowable working pressure, the MAWP, should be, which welds are permitted, and which tests must be performed before equipment enters operation. And here's a detail that most people outside engineering never realize. The U stamp on an ASME certified pressure vessel is not decoration. It is the guarantee that that equipment was designed, manufactured, inspected, and tested following one of the most rigorous safety codes in the world. A vessel without that stamp in an application that requires certification is a ticking time bomb waiting to go off. But ASME doesn't work alone. The American Petroleum Institute, the API, stepped in to complement design standards with standards for operation and inspection. API 510, for example, defines how to inspect pressure vessels already in service. It establishes the acceptable corrosion rate, the frequency of inspections, and the criteria to determine whether a vessel still has enough remaining service life to continue operating safely. API 520 and API 521 address something critical: pressure relief systems. Those valves you see on refineries that open automatically when the internal pressure exceeds the safe limit. They are the last lines of defense before disaster. And when they fail, or when they are ignored, the result can be catastrophic. OSHA, the Occupational Safety and Health Administration, closed the circle with Process Safety Management, known as PSM, governed by Standard 1910. 119. PSM is not a technical design standard. It is a management standard. It requires companies to identify all processes involving highly hazardous substances, analyze the risks, document procedures, train workers, and establish emergency response plans. In theory, an industrial system that fully follows the ASME BPVC, the API standards, and OSHA PSM should be virtually immune to catastrophic accidents. In theory. But here's what nobody likes to say out loud: standards don't execute themselves. They depend on people. And people make mistakes, cut corners, ignore warning signs when they are overloaded, when the pressure to produce is greater than the pressure to be safe. That is where the system breaks. And that is where lives are lost. Now we reach the part that made me stop and take a deep breath before writing. Because this is not theory. This actually happened. With real people. With real families. And it could have been prevented. It was an ordinary morning in Texas City, Texas. The BP refinery, one of the largest in the United States, processing more than 460,000 barrels of crude oil per day, was restarting its isomerization unit after a maintenance period. Isomerization is the process where low-octane gasoline components are chemically transformed into high-octane blending components. Industrial routine. Done hundreds of times before in that same unit. At 1:20 p.m. on March 23, 2005, an explosion of devastating proportions tore through part of the refinery, killing 15 workers and injuring 180 others. The cloud of fire and smoke was visible for miles. Property damage reached into the billions of dollars. And in the months that followed, investigations by the U.S. Chemical Safety Board revealed something deeply disturbing. This was not an accident. It was an announced disaster, built brick by brick through a series of misguided decisions, maintenance failures, and a corporate culture where safety had been pushed aside in favor of production pressure and cost cutting. Let me tell you exactly what happened, because the technical details are essential to understanding the magnitude of the failure. The team was restarting the isomerization unit. The central piece of equipment was a 164-foot-tall distillation tower called the raffinate splitter. That tower needed to be filled with liquid hydrocarbons to a controlled level for the process to work correctly. There is a minimum level, there is a maximum level. And there is a level indicator inside the tower that tells operators where they stand on that scale. The problem? The level indicator was malfunctioning. It was displaying a normal reading while the tower was being dangerously overfilled. The operators, trusting the instrument, kept feeding liquid into the tower without realizing it was already overflowing internally. The actual liquid level inside the tower reached more than 20 times above the safe operating limit, a situation that no safety system should have ever allowed to occur. With the tower completely filled with liquid under high pressure and temperature, liquid began to be forced out through the top of the tower, overwhelming the pressure relief valves. Those valves opened, exactly as they were designed to do, and began discharging liquid and vaporized hydrocarbons into the blowdown drum, that pressure vessel designed to receive and contain those emergency discharges. But there was an additional problem equally serious. The blowdown drum was corroded, had not been adequately inspected in years, and most critically, it was not connected to a flare system, those industrial torches that refineries use to safely burn off relief gases. Instead, the drum vented directly to the open atmosphere. The result was the creation of a massive cloud of highly flammable hydrocarbon vapor at ground level, spreading around the unit. An invisible cloud, heavier than air, silently drifting for dozens of meters in every direction. And at that moment, workers were inside temporary trailers parked just a few meters from the unit. Trailers that should not have been there according to BP's own safety standards. But that remained because management authorized their presence despite the warnings. Ignition occurred at 1:20 p.m. A vehicle, a spark, some heat source, investigators never determined the exact ignition point, was enough to detonate the cloud. The explosion generated a pressure wave that completely destroyed the trailers. 15 people died instantly or within minutes. Most were inside or around the trailers. Some never had time to understand what was happening. Eva Rowe was 20 years old when she got the news. She was at a gas station 45 minutes away from the refinery when a stranger mentioned the BP explosion. She called her mother. No answer. She called her father. No answer. Both of them worked at the refinery. Both of them died that day. That story stops me cold every single time I read it. Because what the Chemical Safety Board uncovered in the weeks and months that followed was that there was no single cause. There was a chain of linked failures, each one individually detectable and correctable, but together creating the perfect conditions for disaster. The faulty level indicators had been reported previously, but never fixed. The corroded blowdown drum had been identified in earlier inspections, but kept in operation. The temporary trailers were in a location prohibited by safety standards, but were authorized to remain. The flare system, that last line of defense that would have burned the vapors before they reached ground level, was disconnected on that specific unit, replaced by simple atmospheric venting, a decision that clearly violated the spirit of API 521. And underneath all of it, the investigation revealed that BP had systematically cut its maintenance and safety budgets in the years before the accident, prioritizing production over integrity. The Chemical Safety Board concluded that BP violated the fundamental principles of OSHA process safety management. The Baker Commission, convened by BP itself and chaired by former Secretary of State James Baker, found evidence that the corporation had systematically failed to identify and correct safety problems across its American refineries. BP paid a record fine of $56 million to OSHA, at the time, the largest penalty in the agency's history. But no fine brings back 15 people. The first layer is the structural design itself, calculating wall thickness with adequate safety margins, selecting material certified by ASME Section 2 with traceable and verified mechanical properties, executing welds qualified according to ASME Section 9, performed by formally qualified welders with documented welding procedure specifications and procedure qualification records. Every weld on a certified vessel has a story: who welded it, when, with what process, with what filler material. The second layer is non-destructive testing, covered by ASME Section 5. Industrial radiography to verify the internal integrity of welds without destroying them. Ultrasound to measure wall thickness and detect internal discontinuities. Magnetic particle testing and liquid penetrant inspection to identify surface cracks. These tests are not optional, they are mandatory before any pressure vessel enters service for the first time. And API 510 requires them periodically throughout the entire service life of the equipment. The third layer is the hydrostatic test. Before entering service, every certified vessel must be pressurized with water, not the process fluid, to 1.3 times the maximum allowable working pressure, and hold that pressure for a defined period without any leakage or deformation. It is the final verification before first use. And it is done with water precisely because, unlike compressed gases, water does not store elastic energy. If the vessel fails during the hydrostatic test, the failure is localized and controlled, not explosive. The fourth layer is the pressure relief devices. PSV, pressure safety valves, are perhaps the most critical safety devices in the entire system. They are set to open automatically at a specific pressure, releasing excess pressure before the vessel reaches its structural limit. But simply having a PSV is not enough. It must be correctly sized for the worst-case overpressure scenario, correctly installed, periodically tested, and connected to a safe disposal system for the released fluids, typically a flare system, not a simple vent to the open atmosphere. That is exactly the point where BP failed in Texas City. Today, the technologies available for monitoring and protecting pressure vessels have advanced dramatically from what existed in 2005. State-of-the-art IoT sensors installed directly on vessels transmit pressure, temperature, and level data in real time to control systems that can trigger alarms and even automatic emergency shutdowns within milliseconds. Online ultrasound allows continuous wall thickness measurement without shutting down the equipment, detecting corrosion as it is happening rather than waiting for an annual inspection. Digital twins, digital replicas of the equipment, allow engineers to computationally simulate how a vessel will behave under different operating conditions before any physical problem develops. And risk-based inspection, RBI, governed by API 580 and API 581, has fundamentally changed how industries plan their maintenance activities. Instead of inspecting all equipment with the same frequency, RBI concentrates inspection resources on the equipment with the highest probability of failure and the highest consequence of failure. More attention where the risk is greatest. Less waste where the risk is low. It is data-driven safety engineering, not intuition. I want to close this video with something that will be very useful for anyone working in the industry or studying to enter it: how these standards relate to each other and why none of them, alone, is sufficient. The ASME BPVC, the Boiler and Pressure Vessel Code, governs design and fabrication. When a pressure vessel leaves the factory with the ASMEU stamp, it means the design was calculated according to the formulas in Section 8. The materials used were certified under Section 2, the welds were performed by qualified welders per Section 9, and the equipment passed the non-destructive examinations required by Section 5. The code guarantees the equipment was born right. But equipment ages. It operates in corrosive environments. It accumulates pressurization cycles. That is where API 510 comes in, the in-service inspection standard. It defines the minimum frequency for external and internal inspections, acceptable inspection methods, how to calculate the corrosion rate based on thickness measurements over time, and the criteria for determining whether a vessel is still fit to continue operating. API 510 is what keeps the equipment right throughout its operational life. API 520 and API 521 protect the system against the worst-case scenario, overpressure. API 520 defines how to size pressure relief valves for every possible overpressure scenario: external fire, cooling failure, accidental outlet blockage. API 521 defines what to do with the fluids released by those valves, how to design the flare system, how to ensure that flammable vapors are not discharged at ground level. In Texas City, the failure to comply with the intent of these standards was directly responsible for the creation of the explosive cloud that killed 15 people. And OSHA PSM closes the loop on the human and organizational side. It requires companies to document all processes involving hazardous substances, conduct formal risk analyses such as HAZOP, hazard and operability study, rigorously train their operators, establish safe and audited operating procedures, and create management of change systems to ensure that any process modification is evaluated from a safety standpoint before being implemented. Because the vast majority of serious industrial accidents do not happen during normal operations, they happen during startups, shutdowns, maintenance events, and changes. Exactly what was happening in Texas City. These standards don't live in isolation. They form an ecosystem. ASME handles how you build it. API handles how you inspect and protect it. OSHA handles how your people manage it every single day. Remove any one of those three legs, and the stool falls. That is the lesson of Texas City. That is the lesson every pressure vessel engineer, every refinery operator, every safety professional carries with them. You made it to the end of this video because you're not the type of person who's satisfied with the surface of things. You want to understand how the world actually works, including the parts that industry would rather keep behind closed doors. What happened in Texas City in 2005 was not a fatality. It was the predictable consequence of a system where the standards existed, the warnings were there, and human decisions went in the wrong direction. 15 people went to work that morning and never came home. And the only legacy we can give them is to make sure their deaths taught something. To the companies, to the engineers, and to every professional who works around any pressurized equipment. If you work in the industry, know someone who does, or you're studying engineering, share this video. Not because it's cool to share, but because the next person who learns what you learned today might be exactly who notices a warning sign before it becomes a disaster. If you made it this far, drop a comment right now. Standards save lives. I want to see how many of you actually made it to the end.